about a multi-party functional encryption. Good. And so this is work by Shweta Agrawal, Rishab Goel, and Junichi Tomida, and Rishab will give the talk.
Thanks for that, and welcome back everyone to the in-person session. So this talk could be a nice segue between the empathy session and the functional encryption session. So the talk is on multi-party functional encryption, and the starting point of this talk is the notion of functional encryption itself. I apologize, the font is bad. Maybe it's like the PowerPoint in the system is a little bit old one or not, but okay. So the notion of functional encryption is a very powerful notion of encryption, which allows fine-grained decryption access over encrypted data. And it saw its roots as early as back in 2005. And pictorially, functional encryption can be understood via the following picture. We have, say, three parties, Alice, Bob, and Charlie. Alice has some private data M. Bob has the secret key. And what Charlie wants to know is that Charlie wants to learn the evaluation of the function F on the message M. Now, given encryption of Alice's data, what Bob could do is that Bob could simply supply Charlie with the master secret key. Charlie can decrypt the ciphertext, evaluate the function, and learn the corresponding value f of m. That's great, but that leaks the entire plain text value. What if Alice only wants Charlie to learn f of m and nothing else? So functional encryption basically was devised to sort of capture this intuition, where the idea was that Bob can actually create some partial decryption keys called functional secret keys, such that given a functional secret key, Charlie can actually compute this on its own without outsourcing this computation to Bob, or with even Bob being offline. And functional encryption lets us solve this problem. The intuition behind functional encryption is basically given a ciphertext that encrypts some data X and polynomial many secret keys, all the university can learn is by running the decryption algorithm and the evaluation of the functions on that particular secret value X. Now, functional encryption has been a grand unifier and has been able to sort of unify all existing encryption functionalities devised at the time, such as identity-based encryption, attribute-based encryption, inner product functional encryption, and much more. And even beyond than just unifying, it has been able to even focus interesting encryption models, such as partially hiding functional encryption, and also has been used as an interesting abstraction to study more fundamental cryptographic objects, such as also using as an abstraction to study program obfuscation and more. And it has been so powerful that functional encryption has even been studied in more powerful models of multiple users. Now, at this point, you might be wondering, okay, hey, isn't functional encryption already like a multi-user model? Even in my simple example, I had like 3 different users. Why do I feel like functional encryption traditionally is like a single user model? The point is that over here, if you really look at the decryption algorithm, it takes as input a single ciphertext and a single secret key pair. But what if the number of ciphertexts could be multiple? They could be multiple different sources of ciphertext. Or what if there are multiple different sources of secret keys? Or maybe both, multiple ciphertexts, multiple secret keys. Traditionally, the notion of functional encryption does not capture these scenarios. And to sort of study these scenarios, the notion of functional encryption was studied in sort of these multi-user models. So for example, one of the earliest works by Wasser et al., they proposed the notion of multi-input functional encryption, where as the name suggests, you have multiple different input sources. You encrypt ciphertext for these ciphertexts independently for these different inputs. And using a single functional secret key, you can learn the evaluation of the function F on the joint inputs together. And this has been recently extended to the notion of multi-client functional encryption. Similar progress has been done in the notion of distributed secret keys, where you have studied multi-authority functional encryption, decentralized functional encryption, and much more. And so much so that we've also studied functional encryption in more powerful models where you can distribute ciphertext as well as secret keys. And the notions of decentralized multi-client functional encryption, ad hoc MIFE, dynamic decentralized functional encryption, a lot of such notions have been studied in the literature. And basically the point is that we have so many different models where we sort of model functional encryption in these multi-user models. And all of these different models have been studied because we have different applications today with different security models. So thus for these different goals, we sort of come up with a different notion of functional encryption primitive for these particular models. While this is quite great, it seems somewhat similar to what the story looked like in the pre-functional encryption days, where we studied encryption for different different models, and we sort of built a new encryption primitive for each of these models. But it turns out in these multi-user models, it's hard to compare which results are known under what models, what are the feasible results from standard assumptions, what functionalities are easy to do, or how can we sort of compare techniques across these different domains. To that end, we sort of try to make progress and trying to understand, can we sort of unify all these results and visualize functional encryption, even these multi-user models, in a single framework? And that's basically our quest, trying to unify and sort of forecast interesting functionalities in the multi-user environments. And to that end, in this work, we introduced the concept of multi-party functional encryption as a broad unifier over all these encryption functionalities. We propose some interesting multi-user encryption functionalities, which had not been previously considered, but seem very meaningful. And we also give new constructions from from a lot of standard assumptions. So just quickly before I'll just tell you how we actually formalize the notion of multi-party functional encryption to give you some intuition. So the point is that we will have sort of two classes of inputs and ciphertext, and we sort of in each secret key and each ciphertext we encrypt or encode inputs. And the point is that the decryption algorithm is going to take as input a polynomial number of ciphertexts and secret keys. And the question would be, how can we potentially, the decryption algorithm, how will it combine the algorithm? There is no notion of functions existing anywhere. So simply we say, okay, hey, imagine that the scheme is associated with an aggregation function with the input class as well as with the ciphertext class as well as the secret key class. And the point will be the aggregation functions are tied to the scheme, and the decryption function is going to evaluate the following function. It's going to aggregate the ciphertext first using the aggregation function. It's going to aggregate the secret keys using secret key functions and then apply the universal circuit. So trying to capture all possible functionality. It doesn't matter if you're working in the ciphertext policy, key policy domain, whether you have multiple inputs, multiple keys, whatever, you should be able to sort of capture all these different notions under a single unified framework. And so pictorially, this is basically you pass the inputs, the ciphertext inputs to the aggregation function X, the Y inputs to the aggregation Y, and apply the universal circuit. And that's basically equivalent to applying the decryption circuit on the encoded and encrypted values. And syntactically, this basically means that the setup algorithm is going to take as input these circuits, which specify the particular scheme. And now the setup algorithm can also be run in three modes: a central mode and a local mode and an interactive mode, and generate these encryption keys. And the idea is that the central mode is going to dictate whether this setup is being done by a single trusted party. A local mode is going to say, okay, it's a non-interactive thing done by everyone independently. And interactive could be a protocol between users. So depending upon that, you can appropriately capture all encryption functionalities. And the security can also be intuitively captured by saying you cannot learn anything beyond what you can learn by running the decryption algorithm. I'll sort of refer you the paper for more details. But basically, in sort of to supplement that, we also sort of propose some interesting new results, such as we built a multi-authority attribute-based inner product function encryption scheme. So this is not a non-trivial combination of a multi-authority attribute-based encryption scheme and an inner product function encryption scheme. Typically, attribute-based encryption is just like an all or nothing primitive. Inner product function encryption is like a functional encryption primitive. Trying to combine these things and also working in a decentralized model where we can actually have multiple authorities. This was not previously studied, and we were able to sort of build new constructions for this in the using bilinear groups. And we were able to also provide some other interesting results in the paper. And I sort of lead you to sort of look at the paper for these interesting results. We're just trying to conclude. So in this work, we propose this notion of multi-party function encryption, and our goal is just to understand function encryption in the multi-user models and trying to compare different techniques and different ideas and trying to sort of juxtapose them so that we can build new interesting functionalities, which should be feasible but have not been studied so far. And this raises many fascinating open questions, which we also had in the paper, and we sort of built some interesting functionalities from time assumptions. So thanks for your time.
Any questions?
There appear to be no questions online.
Quick question. So is there inherent possibilities if you, instead of having aggregation of the two pieces separately and then combined, if you wanted to do something even more global?
So the question Elliot is asking is that we had like this aggregation function working independently on the ciphertext and secret key inputs and then applying the universal circuit. But she's saying, what if you sort of try to imagine that the ciphertext and secret keys are first aggregated together and then something else is happening? All of those can be captured via this framework itself, because you can imagine the aggregation function can simply copy one of the inputs as part of the aggregated function, and then you can apply something on top of it. So that's why it's like it's going to capture also. Basically, the idea is just trying to capture everything and then trying to see, can you come up with interesting functionalities which might be interesting for applications, and then try to see whether we have techniques to actually build this particular functionality or not. So thanks for the question.
Further questions? Okay, let's thank Rishab again.
Okay, the next presentation is about succinct LWE sampling, random polynomials, and obfuscation. This is a work by Vinod Vakunthanathan, Willy Quash, Daniel Wicks, and Hotek Wee, together with Lalita Devidas, and Lalita will be giving the presentation.
I'll start by defining the notion of indistinguishability obfuscation. We think of an IO scheme as some randomized compiler that takes a circuit C and produces an obfuscation of that circuit. We want that the obfuscation will compute the same function as the original circuit, and also that for any two functionally equivalent circuits, i.e. circuits with the same truth table, we have it that their obfuscations are computationally indistinguishable. We've seen in recent years many applications of IO, leading us to believe that it might be some sort of central hub for cryptography. In any case, it become very important for us to understand exactly which assumptions are needed in order to build IO. Currently, we have some state-of-the-art IO schemes which are based on bilinear maps in addition to other assumptions. These are not post-quantum secure. Also, as I said, we do want to understand exactly which assumptions are necessary, which leads to another line of work on plausibly post-quantum secure IO based on LWE-ish assumptions. There's initially some work that was done for heuristic constructions without a proof of security. More recently, we've seen some works that do have security proofs, but based on interactive and or non-falsifiable and particularly complicated LWE-like assumptions. These assumptions are broken for specific implementations depending on the way that they're shown, which is why we're basically motivated to try to clean up these assumptions as much as possible. The point of this work is to try to base IO on an LWE-like assumption that is non-interactive, that is falsifiable, and as simple as possible. In our work, we'll define a new primitive, which we call a succinct LWE sampler. This is a weaker security notion than the notion in WW21 of the oblivious LWE sampler. We'll also show a local to global security amplification theorem. This is our main theorem, which shows that to protect arbitrary computation, it's actually enough to protect one in operation. And I'll go into a little bit more detail about what this means later in the talk. And lastly, we show a candidate construction of a succinct LWE sampler with the security based on random polynomials. And we do
Excuse me, TCC, I believe you have lost your internet connection. The speaker has frozen on our end.
Thanks, Kay. I thought I didn't know if it was me or was some, on the far end.
I also wondered if it was me. We have really high winds today. Just hang tight, everybody. Hopefully we'll be back soon.
Is the connection back?
Yes, it is.
Okay. So at a very high level, we're going to encrypt the program with some sort of homomorphic encryption.
Please forgive me. You've lost your screen share, so you'll need to share screen again. Yes, that's good.
Then to evaluate the program on, to retrieve the truth table of the program, we'll homomorphically compute, basically using FHE evaluation on the ciphertext, evaluating being the function f, which takes some program and evaluates the program on all possible inputs and outputs its truth table. Lastly, we'll just decrypt to recover the truth table of the function. How do we do this? So one idea that seems good at first is to release the randomness that was used in the FHE encryption of the truth table of pi, as opposed to revealing the secret key, which is obviously not secure. However, this is also actually not secure. In my truth algorithm in a recent work, you can actually retrieve. If you look at the way that basically you can retrieve the original things and learn something about the original function pi solely from the randomness used in this encryption. To solve this problem, we'll introduce our new notion of succinct LWE sampler. The idea behind this is intuitively just that we should be able to sample some short seed and then later expand the seed including using the CRS into a larger LWE sample for some matrix A. The way that this solves our problem is that then we can now, still using this regular FHA encryption at first, again, regular homomorphic evaluation to compute the encryption of the truth table of pi. But then to decrypt, we'll include expanding the seed B to LW sample B star. And then we'll add in this LW sample B star in order to mask the randomness R pi, which originally was what was the problem, revealing R pi was not semantically secure. Now we can mask it with some truly uniform S star. And so eventually we'll just get out pi, the truth table for pi with the error E pi and plus E star, which will be basically the security notion that we need later on E star, is that it's big enough to flood E pi. And then finally you finish round to recover the truth table of the program. Let's think about exactly what we need of the security notion. So starting from WW in their oblivious OBE sampler, they required that given the seed for B star and the matrix A, B star should look indistinguishable from fresh LW samples, which by fresh LW samples, we mean where S star is truly random and E star is Gaussian, like you would want when sampling an LW sample for A. However, this requires a simulator, and like I said before, it's broken for specific implementations of the homomorphic decryption circuit. And so that's why we're going to look at a different security notion. What we really need is just that E star is a good flooding distribution. To quantify this more formally, this means that for all functions and inputs such that the output of the function on both inputs is the same, we want that it's indistinguishable if even given the seed for B star, encryption of the input. And then, so here we think of, so E sub F and X0, X1 is the error that results from homomorphically evaluating F on the encryption of X. And so we want that E star is enough to flood the error seen here. However, we're still not really happy with the security notion because it quantifies over all F and is not falsifiable. So the main theorem, as I mentioned in our paper, is a local to global theorem, which shows that it suffices to protect a single AND. This means that we can just look at the case where the F that we're considering is and the inputs are 0, 1 and 0, 0. So again, these are the resulting errors from homomorphically evaluating AND in these ciphertexts. We show that we can upgrade this to strong security, which is what I mentioned before. The trick that we use here is implicitly used in WW, but here we abstract it out and show a hybrid argument to actually upgrade security for a single AND to fully strong security. So the actual construction of our scheme, as I mentioned, relies on random polynomials. The big question that we have is how do we generate E star from a succinct description to still have enough entropy to be able to flood? We have the idea to use random polynomials that are seemingly similar to JLMS19 if you're familiar with that work. However, our parameter settings are actually quite different, which makes our use of the random polynomials different here. Intuitively speaking, we just want that, the tensor of some smaller matrices E1 through D. But if we take that to be E star, we should hope that this looks pseudo-random. How does this actually work in our construction? I'll just briefly give the idea is that we will generate more LW samples by tensoring. So we think about the seed for B star being being matrices, basically LW samples for smaller matrices A1, A2. This is a small example for D equals 2. If we tensor these together, we can rearrange and use the mixed product property to then basically have some A, which depends only on the AIs, and some S star, which depends on both the SIs, the BIs, and the EIs. And finally, our E star term will depend just on the EIs and the tensor of these. This is abstracting away a lot. We're actually multiplying on either side by large matrices that we keep in the CRS and also doing some re-randomizing. But this is a little bit of intuition for how we're actually able to construct this candidate construction where the terms of E star are going to be random polynomials in the terms of the EI. Thank you.
Any questions?
So just a quick, so okay.
The microphone isn't visible.
Apologies for the delay. There do not appear to be any questions online.
Good to know. But okay, so the question is that so this assumption or the way you sort of sample sort of these plugin nuances, this makes sense if you want to sort of obfuscate all functions. But would it make sense to sort of start with simple functions like only basic function classes? Like we already have from LLD optical obfuscations, like these special types of obfuscation schemes. So how do you think they might be hoped to simplify the assumption?
Yeah.
Move to those classes and then maybe like see that okay, this is a provable.
That's definitely something we're looking at in terms of future directions, especially because there's a lot of applications for IO for restricted function classes, things like quantum money and so on and so forth. And so that's definitely something that we're looking into if we can like simplify these, yeah. In the cases of just like a simpler function app instead of this all program.
So,
But we haven't done that. We're still like working on that.
so that means of changing the distribution of how we sort of sample these sort of error distributions, or?
So it's more that I think we would hope to be able to actually prove that this, we would be able to like simplify the assumption more, given with the same construction, be able to simplify the assumption that we're making based on the fact that we're just, only doing obfuscation for some restricted function class. We'd be able to actually do like a little bit more work to simplify the assumption more and maybe make it more like well-studied assumptions rather than something that's, still like quite, it's not as ugly as it has been before, but we still are, like dealing with some polynomials that we're not as familiar with in the mathematical speaking.
And I gathered that was a rather in-depth question, but if you could give those of us online a little bit of context for it, I think, had a little bit of trouble hearing the question.
Oh. Can you repeat the question?
Oh, yeah. I guess, do you want to read the question?
So I guess the question was basically trying to understand this sort of assumption is about if you want to prove security of the full obfuscation scheme, but if you're sort of interested in the obfuscation for a very restricted class, for example, you already know from LWE, lockable obfuscation or point obfuscation, then how does this assumption can be simplified, and what hope is there to actually use this framework to prove security of obfuscation for those specific function classes, and whether this framework, this idea of flooding could be used to prove security in that case. I think that's what Lali was sort of elaborating on.
Great. Any further questions? Not, let's thank the speaker again.
That's my slides. I didn't test my slides. I think it looks okay.
Excellent. Okay, the next talk will be ABE for DFA from LWE against bounded collisions revisited. And this is work by Ho-Tech Wee, and Ho-Tech Wee will be giving the presentation.
Thanks, Gillette. Let me just make sure this works. Oops. Okay, great. All right, so let me start by talking about ABE, attribute-based encryption. So attribute-based encryption, you have a ciphertext associated with attribute X and a message mu, and secret keys are associated with functions. And the basic correctness requirement is that you can decrypt and recover the message mu whenever f of x is equal to 1. And security says that if f of x is 0, the message mu should remain hidden. And this should hold even in the presence of collusions, where the adversary may be able to get hold of multiple secret keys for different functions, as long as they all correspond to 0. All right. So the main new result of this work is, as in the title, a new attribute-based encryption scheme for DFA's deterministic finite automaton from the learning with errors assumption. Right. So our construction is new in the sense it's somewhat different from prior constructions. In that it's actually inspired by pairing-based ABE schemes for DFA. And compared to previous LWE-based schemes, it's simpler and algebraic and avoids the use of ABE for circuits. Right. So in particular, this is the parameters that our construction achieves. So the scheme is actually for the setting of bounded collusions. So there's an a priori bound beyond the number of collusions, number of secret keys, as we can see. These are the parameters that our scheme achieves. And the thing to bear in mind is how it compares to our prior constructions. So we improve on the ciphertext size, so we have a better dependency on the length of the attribute and the collusion size. The secret key size remains the same, and then we get qualitatively better hardness assumptions in that our construction relies only on a slightly superpolynomial modulus to noise ratio for LWE, as opposed to a quasi-polynomial modulus to noise ratio. And what's also nice here, I think, in the construction is that along the way we introduce a new lattice trapdoor. And finally, our construction also extends naturally to give us to the best of my knowledge, the first candidate for a post-quantum ABE for DFA for unbounded collusions. So for this talk, I'm essentially going to only focus on the first two bullets. So let me give you a quick sense of how our scheme looks like. So, so we're going to focus on our DFA for the binary alphabet, which is 0 and 1s. The input is a L-bit string. Okay, so the input X to it, that's the attribute also the input of the DFA. And we are going to specify DFA by a pair of transition matrices. So if Q is the number of states in the DFA, then the transition matrix is just a Q by Q matrix. One for the alphabet 0 and one for the alphabet 1. All right, so our setup algorithm is going to generate a pair of LWE matrices, A0 and A1. It's going to be double the height of what you expect LWE matrix to be, so it's 2n by n. Basically, when you encrypt, you're going to pick many LWE secrets, basically one LWE secret for every bit of the input X. Key generation will pick Q vectors, one vector for every state in the DFA. So the basic decryption invariant is going to be the case that for every I, if after reading the first I bits of the inputs, you reach the state U sub I, you're going to be able to compute an approximation of S sub I times D sub I. D sub U sub I. Right? So the state called the D vector corresponds to the state UI, and then the I secret corresponding to the VI. And the way we achieve this invariant is that we're going to essentially only just compute the substantive differences between these values, and then you can just essentially do a telescoping sum. Right? So that's basically what we're going to do. And to compute the substantive difference, what we're going to do is that in the ciphertext, we're going to publish an LWE sampler. So here the squiggly underline corresponds to adding noise. I'm going to publish an LWE sample where the secret is the concatenation of S sub I minus 1 and S sub I. All right, so this explains why the height of our matrix is 2n. And in the secret key, we're going to give out short Gaussian vectors so that the product of this LWE sample and this short Gaussian vectors is this substantive difference that we're looking for. Okay? So this is basically what our scheme looks like. Now, in the key generation, when we generate the secret key, we're not going to know what U sub I is going to be. So we're going to give out this short Gaussian vectors for all possible U sub I's, which can be described succinctly by this expression. And we actually don't know what X sub I is going to be. So we're going to give out this Gaussian vectors for every possible X sub I. So for 0 and for 1. So this is basically what our scheme looks like, ignoring endpoint conditions of how you do the initialization vector and how you mask the message. Right. So, so what does the security look like? So basically in our security proof, we're going to show that these LWE samples are pseudo-random, even given these short Gaussian vectors in the secret key. Okay. So to do this, first we're going to expand the LWE sample. So we're going to use bar A to denote the top half of the matrix A, and underline A to denote the bottom half of the matrix A. Then this LWE sample can be written as essentially the difference of the LWE samples. Right. Now, if you want to show that the difference of these two LWE samples is pseudo-random, it suffices basically to show that the first term in this difference is pseudo-random. So it boils down to showing the following lemma, which we're going to show from the LWE assumption, namely that if you have this matrix A of dimension 2n times m, if you're going to look at the top half of A, which we call A overline, if we take S times the top half of A, it's going to be pseudo-random, even given an oracle that given the matrix n computes these Gaussian pre-images for a random matrix T. Okay, so this is roughly what we're going to show from the LWE assumption. All right, and we're going to actually show, our proof gives us something stronger. We're actually able to handle an oracle that not just take a matrix M, but also an additional matrix C, that's like an offset matrix, so that the bottom half of the pre-image is going to be the n times C. And this is going to be this is actually a generalization of the previous computational lemma or target something like that from some fireworks, which corresponds to the special case where the m equals 0. So the main complication in our setting is the fact that this bottom half of the pre-image could depend on the top half of the pre-image. Right? And the proof basically, to prove this statement, we're going to introduce a new notion of a half trapdoor for LWE. So a half trapdoor for LWE is actually a low norm matrix, such that A times this trapdoor matrix is a 0 on top, stacked on top of the scheduled matrix. Okay. And basically the key novelty in the proof lies in showing that given this half trapdoor, you can simulate this oracle. So we give a new sampling algorithm. And the way this sampling algorithm works basically proceeds in 2 steps. First, we show how to sample a related distribution, where instead of D times M at the bottom, you have N times D. All right. This distribution turns out not to be too hard to do. If you sort of know this is your goal in mind, then it basically follows from more or less standard LW techniques. So we'll skip this part. And then the second step lies in sort of bridging this gap between M times D and D times M. And the way we do this is we use this vectorization operator from linear algebra that essentially allows us to switch the order of multiplication from D times M to N times D, and then we can reduce to the previous case in bullet point. Okay. All right, so let me now summarize the main result of this work. We get a new ABE from DFA from LWE with improved parameters. Along the way, we have this new half-trapdoor idea, and we also actually get a candidate for unbounded collision as well. So a couple open problems. One is do a quick analysis of our new candidate for unbounded collisions. I think that would be nice. Another is to see if our techniques can be extended to give simpler constructions for Turing machines. Thank you.
Questions for Hojak?
There appear to be no questions online.
Yeah.
Oh, there is?
No.
No.
Wait,
Okay. Great. All right.
But wait, I have a question.
Oh, yeah. No.
Yeah, just a high-level question. Can you
Okay.
say something about like how much more complicated do you think it'll be to extend to Turing machines?
How much complicated it will be to get the Turing machines? Or to the question, how much more complicated it will be to get the Turing machines? So it depends. So basically, if you have a bounded space Turing machines, then I think it's not so hard because you can basically, if you have bounded space Turing machine or log space Turing machines, and you allow your ciphertext size to grow exponentially in the space, then that's a little easier because you can essentially enumerate over all space configuration that sort of looks like states in the DFA. So the hardest setting is sort of to get Turing machines for bounded space, but with a polynomial dependency on the space requirements. And this seems a bit hard with our current framework, although such a scheme is known in the prior work of Agrawa and Singh, but the construction is a bit more complicated and passes through ABE for circuits, and it doesn't lend itself to a natural candidate for the unbounded collision setting. So at the bare minimum, that actually should be some really, really nice ideas in there. So at the bare minimum, we'll need to marry our construction with some of these ideas in the other work.
Okay, let's thank Hojak again.
Okay, so we saw yesterday, I guess, a long teaser that referred to this work, but today we'll see an additional 5 minutes about it, about disappearing cryptography and the bounded storage model. This is a joint work between Jiaxin Guan and Mark Zandri, and Jiaxin will give us the talk.
Thank you, Chair, for the introduction. So my name is Jiaxin Guan, and today I'll be talking again about disappearing cryptography in a bounded storage model. This is a joint work with Mark Zandri. Both of us are from Princeton University and NTT Research. So as you can probably tell, the title consists of two parts. The first part being disappearing cryptography. So what do we mean by disappearing cryptography? Well, let's see this through two motivating examples. So in the first example, we have Alice and Bob, and Alice is sending over some encrypted document over to Bob. And here comes our eavesdropper Eve, who comes and makes a copy of the document. And then at a later time, maybe a week, a year, 10 years later, Eve is able to somehow extract a private key from Bob, either through social engineering, interrogation, or security breaches. And then what Eve can do is to simply use the key to decrypt the document and obtain the original message. So to prevent against these sort of attacks, what we want is what we call forward secrecy, essentially saying that a secret key leak in the future should not compromise the security of the messages that are sent before. However, in the standard model, in order to have forward secrecy, we will either require constant key updates or we will require the two parties to have interaction. And both of these could be undesirable in many scenarios. The second example is also quite similar. Alice sends over encrypted document, the eavesdropper makes a copy. Then at a later time, Eve is going to ask Bob for a private key. However, instead of providing the actual private key, what Bob can do is to provide a fake private key, which will still allow Eve to decrypt the document, but this time to a fake message, for example, a cute picture of a cat. So what we refer to this is receiver deniable encryption, essentially saying that the receiver can provide a fake key to have it decrypt to a fake message. So again, in the standard model, to achieve receiver deniable encryption, we would require a multi-round interactive protocol between the honest parties. So with disappearing cryptography, we aim to solve these two problems altogether. But how exactly? Imagine this. So suppose Alice sends over the document over to Bob, and Eve comes and makes a copy. Then, through some magic, this ciphertext just magically disappears. Then at a later time, even if Eve is given the actual private key, there's nothing he can do. There is no ciphertext for him to decrypt. So by default, this has forward secrecy, and it is also vacuously receiver denied. But how exactly do we make the magic happen? So we resolved to the bounded storage model, first put forward by Yuri Maurer in 1992. What does the bounded storage model say? Well, traditionally in cryptography, when we talk about an adversary, we imagine the adversary to be time bounded. So namely, the adversary needs to finish its task within time polynomial in the security parameter. However, in a bounded storage model, the adversary can take as much time as he wants, but the adversary is bounded by the total number of memory bits that he can ever use. And usually we will have the bound to be a fixed polynomial on the security parameter. So the idea that we take is, imagine if we set the size of the ciphertext to be way larger than the adversary's storage bound, then there's when the ciphertext is being sent, there is no way that the adversary can write down the ciphertext. Therefore, for the adversary, the ciphertext effectively just disappears right after the transmission ends. Using that intuition, we initiate the study of disappearing cryptography by investigating 4 different schemes. So we start off with a disappearing PKE scheme corresponding to the example that we have just seen, and we further extend it to disappearing functional encryption. We also study disappearing signatures, where the signatures are too large to store for the adversary, as well as online obfuscation, where we imagine we stream programs that are too large for the adversaries to store. And in fact, we show that online obfuscation can be a useful tool by showing how to construct the previous 3 using online obfuscation as a building block. So the security definition that we adopt for online obfuscation is a flavor of virtual gray box, VGB obfuscation, which is a middle ground between indistinguishability obfuscation, IO, and VBB obfuscation, virtual black box obfuscation. We also have similar definitions for an online obfuscation with IO and VBB security, and we have shown that VBB obfuscation is also impossible for online obfuscation. Furthermore, we provide 2 different candidate constructions for an online obfuscator with VGB security. The first construction is based on large matrix branching programs, which is a common technique used in constructing IO. And the second candidate construction is based on the timestamping scheme in the bounded storage model. So in terms of future directions, so usually the way people use bounded storage model is to prove things information theoretically. However, in this paper, what we did is we combined computational assumptions together with the bounded storage model, and this allows us to achieve never before possible results, effectively having these different schemes in the disappearing cryptography. So we think it will be an interesting problem to explore what other classically impossible results can be overcome by combining the bounded storage model together with computational assumptions. And secondly, we initiate the study of online obfuscation. And just as standard model obfuscation turns out to be a very powerful tool in the study of standard model cryptography, we have shown that online obfuscation is also a central tool in the study of disappearing cryptography in the bounded storage model. Although our constructions are only candidate constructions and do not have full security proofs, we want to mention that the standard model obfuscation also started out as security conjectures. So we hope that future work will be able to improve the state of the candidate constructions. And that's it for the talk. Thank you for your time.
Questions?
No questions currently online.
Once again, I have a question now. Can you say a little bit about the syntax of online obfuscation? How does it compare to standard example?
Oh yeah, the syntax of the online obfuscation is essentially we imagine the security game having two types of rounds. So there's interaction round where we have so essentially there's two games. In the first game, the challenger interacts with the adversary, and in the second game, the challenger interacts with the simulator. So we want the challenger to be unable to distinguish between whether it's interacting with the challenger, interacting with the adversary or the simulator. And what the adversary gets to get a stream of the actual obfuscated program. What the simulator gets is to actually get queries to the original circuit. So yeah, so that's sort of how we imagine we define things. So essentially, instead of getting the stream program, the simulator only gets to query the original circuit. Yeah, there's a full security definition in the recorded video talk.
Right, there's a question here from Brent. I'm not sure if they hear this microphone. Go give it a try.
Well, maybe you can repeat it. Or I'll try my best. So do you have any sense of the numbers needed for the bounded storage model? Like just like what type of speed of internet connection and how limited would the storage have to be?
Okay, yeah. So the question is about like the size of in terms of the numbers of the bounded storage model, like what's the bandwidth requirements in terms of adversary storage. Right. So usually, so essentially, most of the work has a quadratic gap between the adversary space and the honest party space. For example, think about the honest party space being 10 gigabytes. In that case, the adversary storage will actually be in the scale of zillion ZB. That's like beyond petabytes. So that's like a huge amount. Although, like, we do want to point out that the bounded storage model, they inherently have a high communication cost because the whole idea is to send a huge amount of information that exceeds your storage. So the communication cost is high, but as we can see, this quadratic gap is already really intimidating because I only need 10 gigabytes of storage, but if you square it, it's going to be a huge amount that is almost impossible for any like normal person to have. The computation costs, here we're assuming computational assumptions. We're using them together with the bounded storage model.
For the honest parties.
But honest parties, yes, it's also low.
To take advantage of that ZB, you would have to send that much.
Yes, if you want to take advantage of that, yes.
Okay, so
Which is not a desirable thing to do.
Any further questions? Not, let's thank the speaker.
Okay, great. The next presentation will be about direct product hardness amplification. This is a work by David Lazenberger and Uri Malo, and David will be giving the talk.
Thank you. So yeah, I'll be presenting our paper, direct product hardness amplification.
Yes, yes.
Okay. Is it okay? Yes. So I start to explain the setting we are interested in. How do I continue? Does it? Yeah, okay, perfect. So we are interested in this kind of direct product construction. So the end of multiple games. So if you have a game, think of as, cryptographic game, say signature forgery game or something similar. You can take the direct product, say the end of two such games, G and H, and then a winner can interact with these two games in parallel. And then So this is a natural construction. You try to amplify the hardness of the game. The hope is that it's harder to win the end of two games than to win just one of the games individually. And this is a natural construction. Of course, obviously, this hardness relates to the actual security of the underlying sort of the primitives you're trying to build. So this, if you can do this, you can basically, you can take a weak primitive, say weak one-way function or something like this, and you can basically get a strong one-way function, or say a strong signature scheme from the weak one. It's a natural thing to do. Right? So the obvious question is somehow is that, okay, you take these games, they're independent. You would hope, you would intuitively expect that the hardness amplifies, hardness amplifies in the natural way. It multiplies somehow, right? The hardness multiplies somehow because the games are independent. Now, in an information theoretic setting, this is known. It's not trivial, but it's pretty easy to prove that actually it doesn't multiply in a perfect way. Okay, for any such games, G and H. This is exactly what you would expect. But here we are interested in the more difficult, more computational setting where what would you need to show? Someone you basically need a reduction, and it's a bit more tricky. You need to assume it's only true for certain kinds of games. It's only true in an approximate sense. Somehow you lose something. You lose actually quite a lot. So the talk is somehow, or this work is somehow about this. Somehow. Like how do you do this? Like this reduction. And before I show some more about how this reduction looks like, I state our main results. So we prove an abstract hardness amplification theorem that is simpler, more general and stronger than previous theorems of the same kind or similar kind. And our focus is twofold. So first, we try to provide close to optimal concrete bounds as opposed to just asymptotic ones. But the idea is that these asymptotic results just follow as simple corollaries to these concrete bounds that we give. And then second, in the spirit of abstraction, we try to distill out the essence of the typical such hardness amplification statement, sort of the argument that is made, and to get a simple and abstract sort of theorem that you can reuse. And we then show this in the second part and apply by applying our theorem to some non-trivial interactive cryptographic games where we can show that actually you can have a more modular kind of analysis, this kind of statement. You can basically inherit the actual amplification from such a theorem. And then this is basically for free. Okay. So let's look at how this reduction that I mentioned before looks like. So here on the left, you have the end of two games, G and H, and the winner can interact with it in parallel. And now the reduction would try to turn such a winner for the end, GH, into a winner for just G, and into a winner for just H, right? So the only black box way you can basically do this at first, sort of, you just say, okay, we simulate an instance of H towards the winner to get this winner WH for G, and then we can do the opposite somehow for H, right? So basically we get actually two reductions, but it's just one towards H and one towards G, right? But now, of course, remember that we're talking about amplification, so we would now like to say, actually, it's easier to win just G, or it's easier to win just H than to win the end of the two games. Of course, this is what we wanted to say, but now if you look at this, of course, you see that, okay, if you just assume any winner, any game, somehow this can be that the winning probability here on the right might be just the same as on the left, okay? So in any such setting, somehow you need to boost the winning probability of these winners, WH, WG here on the right somehow. So this is where you now need to assume very strong structure on the game. For example, you need to assume that you can somehow, you can boost the winner, say by, this is really a standard way to do this. You can basically repeat the winner independently a few times. And it's such that, you repeat a few times. If you win at least one of your few attempts, then you won. Say signature forgery is like this. You can basically attempt many times to forge a signature, and then you're good at some point when you're done, right? So this is, so now let's make an example. Say we have a winner W, right? Wins this AND here with 1%, say delta winning probability. And now the question is, if we do this boosting, right? We repeat few times. How often do we need to do this so that we get the expected winning probability of close to the square root of delta, say close to 10%, say 9.9%? How often do we need to do this to actually get this guarantee? right? So this is sort of, there's a classical way of doing this somehow. And if you run the numbers, somehow you see that you need around 76,000 repetitions. Seems to be quite a lot for such a basic amplification. And the consequence of our new result is that actually 90 repetitions are sufficient. And it's easy to see that 44 are necessary. Okay. So there's no time to actually show the actual result, but it's just display it to get you somehow the idea of the level of where we phrase the result. And it's the main message is that it's just about your expectations over probability distributions. And then some functions, mu and psi here, where psi corresponds to the boosting, and mu corresponds to basically the winning structure of this winner for the diode product that we've assumed. And then we basically relate these two, basically these three expectations here, where we somehow nest in a different way. Somehow this would correspond to the winning probability of the G of G, somehow of the reduction towards G, and this towards H, and this here is the winning probability of the AND, somehow of the two games, somehow showing that this is smaller than these individually. And then, so this is the classical way of analyzing this. We notice that actually a typical way to amplify here is this boosting function psi would be this function here, 1 minus x to the q. Is it just because you repeat q times? It's actually a concave function. If you exploit this in an analysis, then you can actually get a stronger result. Okay. And this is basically where the improved numbers come from. Right? So this is, you just take something stronger. But the main point is somehow really that, you know, everything that happens is at this basic level, just expectations of a probability distributions of some function. Okay. So then obviously we have much more. We discuss the tightness. You can see that what we do is sort of close to optimal, but not quite perfect. Somehow there's still some small gap left. And actually we have a conjecture of what seems to be optimal, at least for certain boosting functions, which is basically very loosely speaking, somehow saying that, you know, either the winning probability or the losing probability of a winner is somehow maximally concentrated. And we would be quite excited to prove this. We think it's doable. And then lastly, obviously, as we said, somehow we have these applications where the details are not that important, but the main point we try to convey is really that you can modularize such an analysis. It's basically the actual amplification you inherit just for free from our amplification theorem. So if you're interested in any of this, you can check out our paper. It's on ePrint. Thank you.
Actually, for lack of time, I'm not going to ask the questions.
Okay, so let's thank the speaker again. Okay, the next presentation will be non-malleable time lock puzzles and applications. This is a work by Cody Futag, Ilan Komogotsky, Rafael Pass, and Naomi Silkin. And Naomi will give the presentation.
Thanks. So yeah, I'll be talking about non-malleable time lock puzzles, and this is joint work with Cody Futag, Ilan Komogotsky, and Rafael Pass. So the focus of this work is the notion of time lock puzzles. And basically what a time lock puzzle allows you to do is hide some value for some amount of time. So given some secret S that we want to hide and some amount of time T, we can efficiently encode S into a puzzle. And this puzzle can be solved in time T, but not faster. And by efficiently encode, I mean in time much, much less than T. One way to think about a time lock puzzle is just as a fine-grained analog of a commitment. So encoding is quick, it's fully binding, but then it's only hiding until time T rather than indefinitely. So the reason that we're looking at time lock puzzles is because they actually give this very simple to state and non-trivial coin flipping protocol. So the setting here is where we have n parties and they have access to some public bulletin board. And the goal is just to flip an unbiased coin. And the protocol is really simple. So first, they each sample a uniformly random value. They commit to their values using a time lock puzzle and post the puzzle on the bulletin board. When all the puzzles have been posted, they can open their values and then just set the output to the XOR. So this is just commit and reveal, but using time lock puzzles instead of commitments. And when everyone is honest, this is going to be unbiased, right? Because we're just taking the XOR of uniformly random and independent bits. But actually this gives something more, which is that even an adversary who tries to abort early or doesn't open its puzzle won't impact the output. In particular, at the end of the protocol, this is timed, we can just solve any unopened puzzle. So refusing to open doesn't bias the output. And in general, without these timing assumptions, this is actually not possible to achieve. So this is a great starting point, fairness against aborting adversaries. And in this work, we extend this to fairness against fully malicious adversaries that behave arbitrarily in the protocol. So let me just give you the high level idea of this. So for the output to be unbiased, what we really need is the values on the board to be independent. So we need to see how an adversary can sample a value dishonestly to try and make these dependent. So let's suppose we have one party here, that's the adversary. And let's say the adversary waits until everyone else has posted their puzzle. So this is the point where we're at in the protocol. And let's see what we can do. So even taking this out of the context of the protocol, basically we have an adversary that is receiving or seeing a bunch of puzzles and is trying to output his own puzzle. And I want to ensure that his puzzle will be to a value that's independent of the input ones. But that's not necessarily the case, right? He could just copy the puzzle. That's not independent. Or maybe there's a much more complex attack where he could combine the input puzzles in different ways to get a value that's related to all of them. The point here is that even though the security of time lock puzzles hides the underlying values, it doesn't ensure that you can't combine the puzzles themselves to one that is to a related value. And going back to our protocol, if you can do this, you can clearly always bias the output. So the security notion that prevents against this type of attack is called non-malleability. It's studied in many contexts and captures all of these types of maybe very complex or arbitrary attacks. And in this work, what we do is we formalize and construct non-malleable time lock puzzles, and we show that they do give fairness in this protocol. So in my last minute or two, I'm just going to tell you about our results. So we give two constructions of time lock puzzles. The first is practically efficient, and it only relies on any underlying time lock puzzle in a black box way, and it's in the random oracle model. The second one is in the plain model, but it relies on stronger sub-exponential style assumptions. So it's really a trade-off here between what you want to assume and what model you want to be in. I will emphasize that we don't have any setup. And in particular for our protocol in the random oracle model, the adversary might receive or is allowed to receive non-uniform advice about the oracle. This is called the auxiliary input random oracle model. So that's the model that we're in. And we use these constructions to get multi-party coin flipping against malicious adversaries. In particular, our protocol has fairness, even against parties that adversaries that control all but one party. It also has this really nice efficiency property known as optimistic efficiency, where if everyone is honest, they don't need to solve any puzzles. So in the honest setting, we sort of get the best type of efficiency for our protocol. We also have a public verifiability property, so the output can be publicly and efficiently verified. And lastly, we can also make our protocol non-interactive.
So just, one round of posting puzzles on the board just by having everyone solve everyone's puzzle. So depending on what you want, it can be interactive or non-interactive with different efficiency trade-offs. Lastly, I'll just note that this is the first protocol under any assumption that satisfies this combination of fairness and optimistic efficiency for this incredibly fundamental task of coin flipping. So we have a bunch of other results. Feel free to see the paper for those or come talk to me. And that's it. So thank you for listening, and I'm happy to take any questions.
Questions for Naomi?
I believe there is a question online, although forgive me if it's not for this talk. It's from Richard Outerbridge. And
it is for this talk.
It is great. Thank you. Would you like to ask it verbally?
Yes, that would be fantastic.
If I can remember it. With regard to timing, where do each or even all of the participants get their trusted or secure time from?
So that's definitely up to the application and how this protocol is being used. We do need, some sort of shared clock or a way to, know elapsed time. So that is the model that we're in. We don't deal with the details of that in this work because it's really up to the application.
Okay.
Further questions? Ivan?
So beyond coin tossing, we know that coin tossing with the black box is not enough for security generally to say, but it can rule out fully secure to see, or can you extend this to some other functionalities beyond coin tossing?
That's definitely a great question and an open question, and hopefully future work for this.
The question was whether you could extend beyond coin tossing for applications to fully secure computation. Thank you.
The general attack for coin tossing is I just copy the commitment rate, so and I can get 0.
So the question was, what do you do if someone just copies the puzzle? So we can just disallow that by, replacing any copied puzzle with a dummy value. In general, in non-malleability, you almost always have this setting where if the adversary copies, we ignore what he did, but otherwise he's allowed to do any sort of attack.
All right, let's thank you again.
Okay, we are now ready for the final talk in this session about rate 1 quantum fully homomorphic encryption. This is a joint work between Orestes Scherduvelis, Nico Dotling, and Giulio Malatova, and Orestes will be giving the presentation.
Thank you for the introduction. So this is I'm Orestes, and it's a work with Nico Dotling and Giulio Malatova titled Rate 1 Quantum Fully Homomorphic Encryption. I'm not sure what I did. Sorry.
Let me.
You know what? Yeah.
No, not a problem.
How do I?
You-
Okay, sure, that makes sense. Okay, to begin with, I'm going to define fully homomorphic encryption, or an FHC scheme. And what it basically is, it's an encryption scheme where if we have Alice and Bob, Alice can send an encrypted message such that later Bob can compute the encryption of f of m for an arbitrary function f. Yeah. So basically, Bob can perform computations under encryption. And the setting where this is very interesting is useful if we have a client, a weaker client that wants to outsource computations to a more powerful server. That's why in the figure, Clark Kent is supposed to be the weaker client and Superman the more powerful server. Of course, in a setting like this, we want to achieve security. So first of all, we want security for Alice, which means that her message M must remain hidden from Bob. So Bob, given encryptions of two different messages, cannot tell them apart. But we also want security for Bob or the server, which translates into circuit privacy. So this means that we want for the circuit used for the homomorphic computation to be hidden from Alice. When talking about circuit privacy, we can refer to either semi-honest circuit privacy, which is basically circuit privacy for only one-fourth messages from Alice, or to this stronger notion of malicious circuit privacy, where circuit privacy holds for any arbitrary message from Alice. For classical FHC schemes, in this paper by Ostrowski and al., they show how to convert any semi-honest circuit private FHC into a malicious circuit private one. Now, apart from security, we also want to achieve efficiency, especially if we want to use these protocols into real-life systems. And the problem is that because of security reasons, there's a communication overhead introduced to the message sent from the server to the client. And we want for this overhead to not be too big so as to nullify the efficiency of outsourcing the computations in the first place. So usually what we need is communication complexity to be compact, which means independent of the size of the circuit so as not to get exponentially bigger. And this is usually enough, and thus FHC schemes are useful in many applications such as secure function evaluation or encrypted databases. And the best communication complexity of an FHC scheme was constructed in this paper by Borkowski and al., where their complexity approach is the one of the insecure protocol, where Alice would just send her message in plain. Now, a metric that we use for communication complexity is rate. Rate is basically the message to ciphertext ratio, or to be a bit more technical, it's the size of the computed data in plain over the size of the homomorphically computed data. And when we refer to a rate 1 scheme, like I did in the title, we refer to schemes that asymptotically approach rate 1, just like the one from Borkowski and al. So we have minimal communication complexity. Now, if we move into the quantum setting, we also have quantum fully homomorphic encryption schemes, which are basically the same thing, but instead of classical messages, we have quantum messages, and both Alice and Bob can be quantum. Much less is known for the quantum setting, but we think that it's even more interesting due to the large gap between the quantum capabilities of regular users and servers on the cloud in the future. And the more interesting case is if the output, the final output from the server is a quantum state, because if it's classical, maybe we can use classical techniques to get minimal communication complexity, but what happens if it's quantum? And the question is, can we get maliciously secure FHC schemes in the quantum setting with minimal communication complexity? And that's exactly what we answer in this paper and what we construct. In order to do this, we have two main technical steps. First, we construct a maliciously circuit private quantum FHC, and we also construct a rate 1 quantum FHC. This can be of individual interest, but they're compatible and we can combine them for a final result. And to do this, we assume only standard LWE with polynomial modulo to noise ratio. And that's it. Thank you.
Questions? Any thoughts on what the next step is?
So like this, we didn't have a specific application in mind. This was basically to match the communication complexity of the classical counterpart in the quantum setting, but I think that this can have many applications, especially in the future where it could be used for real-life systems.
Okay, so no further questions, and we'll conclude this. So please.